Okay, then thank you very much for the introduction, and thanks to all of the rest of you for joining us. Good day or good night to each of you in your respective time zones. We are going to talk today about the NREC agricultural person detection data set. This video that's playing right now is giving you a glimpse of the things to come, but over the course of the next hour, we'll tell you about the motivation, design, and collection of the data set, all the cool things that you can do with it as well. So, as Amy said, there are two of us who will be speaking today. The voice you're hearing right now is Zach Pezzementi. Excuse me, I'm going to tell you about the data set itself and the analysis that we did of it prior to its release, culminating in a paper in the Journal of Field Robotics. Then I'm going to turn it over to Trenton to talk about some follow-on work that we did that makes use of the data set and some other cool things that you can do with it, centered around a paper that we published at the Safety, Security, and Rescue Robotics Conference, another IEEE conference. And so both of us, as Amy said, are from the National Robotics Engineering Center, which is part of the Robotics Institute at Carnegie Mellon. The institution that does a lot of work in agricultural robotics and automation, including both commercial and government-sponsored research. So the stuff that we're going to be talking about today is all government-sponsored things. The work in the first portion of it, sponsored by the USDA through the NSF's National Robotics Initiative, and the follow-on work sponsored by the U.S. Army Test Resource Management Center. So first, a bit of history. The genesis of this work was the development of an autonomous tractor system for a citrus grower in Florida that would carry out autonomous mowing and spraying operations, and when it would encounter an obstacle, such as a person or vehicle, it would come to a stop. So you can see it operating here autonomously, and it has carried out over a couple thousand kilometers of autonomous operation in a real working orchard over its lifetime. So yeah, it would follow a pre-planned trajectory and then supposed to come to a stop whenever it encounters a person or vehicle like that. In the course of evaluating this system, we collected a lot of data to analyze performance of those detection systems, and those revealed some particularly interesting and challenging conditions that were somewhat specific to this domain and environment that motivated future work and a lot of the design of the data set that we're going to present. So for a bit of context, there's been certainly a lot of work in the person detection domain in the field of autonomous driving, excuse me, and a lot of data sets developed to evaluate person detectors in urban environments, on streets, maybe highways. But very little focus on off-road domains, let alone agricultural ones. So despite that, we show comparison of our data set to the most prominent person detection data sets from the literature in all those urban fields. And at least prior to the release of ours, ours was the largest as well as richest in terms of metadata associated with the images provided of all the data sets in this field. So more labeled images, and we have both stereo and continuous video and GPS information for position of the vehicle over time. Since then, Berkeley has released their Deep Drive data set, which has about the same number of labeled images, but still doesn't have stereo, which ours does. So perhaps an obvious point, but there do exist all these data sets for the urban domain. There's still big questions as to whether things that perform well on those data sets would also do a good job in agricultural or off-road environments. So there's an illustration here of the differences between them, may be obvious to you, but these images look quite different, and it's not difficult to tell which domain a given image came from. And one visualization shown here is HOG feature visualization of the gradient structure of local regions of the image. And you can see that there's just a lot more kind of clean structure in the urban images and a lot more gradient energy spread all around in the agricultural images, and the differences between the locations on the person versus the background are also very different in character. So the main point here is it's not clear whether algorithms developed targeting one domain or the other would perform well on the opposite one. And so releasing a data set that focuses on agriculture allows us to spur research in that domain. So here is an overview of the remainder of the talk. First, going to talk about the data collection platform and the locations where we collected data, then the general design and approach for how we were collecting our videos, then go into the way we were evaluating the quality of and accuracy of person detectors, and then the results of that evaluation on some leading approaches. And then we'll switch over to the follow-on work that makes use of the data set in evaluating the robustness of algorithms to particularly challenging simulated conditions, as well as other data that are available as part of the data set. So the dashed lines marked about a third and 2/3 of the way through are the locations where I plan to stop for questions and address the ones that have queued up by then. All right. So as I mentioned, the beginnings of this data set were collected when we were evaluating this previous autonomous system in a Florida orange grove. You can see a picture of the tractor platform there. Excuse me, in the context of the orange trees. And we performed multiple data collections after that, initial evaluation to round out the data and focus more on some of the areas of particular interest that we wanted to evaluate. So that included people standing still, people in motion, carrying out predefined motions, trying to capture a variety of different appearance with people wearing different clothing. The data collection trips that we performed were at a few different times of the year, so we got natural variation in seasons as well as lighting and weather, and having people in various different poses and levels of occlusion from vegetation, which I'll show later on. You can get an idea of where this orchard was in southern Florida, down southwest of Lake Okeechobee here, and then we zoom in on the right, and you can see it's really quite a large orchard, several square miles in size. So even covering a small portion of it, we're able to get a lot of variety of locations represented in the data set. So that is orange orchard data. Then yes, right, the data collection platform is this autonomous tractor system. So you can see the stereo camera that we are using at the center there. There's actually 3 stereo cameras mounted on the vehicle for the full sensor platform of the autonomous system, but we're just using the forward-looking one in this data set. And then behind that a little bit, you can see the GPS unit that's providing location information associated with all the images. Then we also collected additional data at a second environment to provide a little more variety of environments, basically. This time in apple orchards. So allows us to evaluate some generalization between environments, but the focus of the data collection here was largely the same as the previous ones, trying to make them as similar as possible, covering all the same types of varieties of poses and motions, etc. But with a little more focus on people in motion and people in particularly unusual poses. I'll explain more of what that means later on. So in this environment, you can see an overhead view of this apple orchard. It is considerably smaller than the orange grove that we were in before, but still certainly large enough for us to traverse a lot of different locations and get a lot of variety within that. The platform that we used for this was a pickup truck, a little different than the tractor, but logistics of the grove, or rather orchard, were a lot simpler to figure out with that. But we're using the exact same sensor package as on the tractor. So the same stereo cameras you can see mounted up here, and the same GPS just behind it. And these are mounted to give as similar of a view as possible to the view that the images on the tractor provided. So zoom in on the cameras a bit, have a little more information on the types of images that we're getting out of them. These are some custom-built cameras for high dynamic range to be able to handle the large lighting variations we get in outdoor imaging. They do a pretty surprisingly good job with that. 720 by 480 resolution, and some other statistics that you can see there. All of the data that we label in the data set is provided at 7.5 Hertz, but there are actually 15 Hertz images available for the Apple data. If there's something you want to do with that. Okay, so that is the platform. Now, what are we trying to collect? What kinds of things are we trying to record here? I think probably the biggest thing that really separates the design of this data set from the previous ones in all the urban domains, but just in general, is a lot of them are really all of them are pretty much just driving around passively collecting data, whatever they happen to encounter. Whereas this data set is specifically scenario driven, where we are trying to collect particular types of situations. So we have two different types of what we call logs, which are basically video recordings with associated metadata like GPS, et cetera. Ones that we call positive and negative, depending on whether there are people that are visible in them. So the negative logs are ones where people do not appear. So you're just driving around and never seeing anybody. And those are pretty much the situations represented by the vast majority of the data in most of the other data sets. But they form a relatively small portion of our data set, which is more focused on these positive logs, which are situations where you're driving up to people in predefined situations. So they are either standing still or moving, or we have a special category for people in unusual poses. And I'll explain what the specifics are of each of those in the following slides. But we go through a set of all these predefined things and capture logs of all of them for a person wearing the same outfit and consider that to be a log set. So then what are each of these subsets? Static person logs are logs where the person is standing in a few predefined positions with respect to the rows of trees in the orchard. So The general structure of these orchards are you have the vehicle that's going to be driving down a road or down between two rows of trees and performing some sort of operation in the autonomous system. It was doing mowing or spraying. And it might encounter people in a variety of locations with respect to the trees. So we have one that is a person standing kind of up in the trees and partially occluded by them. We have a person who's standing right on the edge of the trees, but should still be fully visible. And a person who's standing right out in the open in the middle of between the two rows of trees. And then the final position is occasionally there will be a tree missing in the row, and the person will be standing in a gap where that tree would otherwise be. So we do logs of each of those locations with people standing up, and then again for people crouching down. And this is what some of those positions look like in real images. So person in the trees, you can see a lot of occlusion right on the edge of the trees, out in the center of the row, and in the tree gap also you can get a lot of occlusion there. So this is what the collection of one of those logs looks like from an outside perspective. The vehicle starts from a stop, drives up to the person, and comes to a stop again. So this is actually driven, the vehicle is being driven by a person in this case, but is trying to emulate basically the ideal behavior of an autonomous system. We also have a variety of predefined motions, and we collect logs of people carrying out each of those motions. So they're illustrated here, but basically things like walking towards the vehicle, either along the center of the row or along the side of it, walking across the row, standing up and walking away, approaching the vehicle during a turn, things like that. And this is what one of those logs looks like. Same general structure, start from a stop, start driving towards the person. In this case, the person is now walking towards them along the edge of the row. The vehicle will come to a stop, and the person continues along past the vehicle. And then finally, we have a number of unusual poses that we try to get good data to represent. So these are intended to represent situations which are not particularly common, but are very safety relevant. So people lying down or people falling over, leave them in vulnerable position, and you would definitely want to be able to handle that if you can, but they're pretty challenging. So we separate them out into their own category. And then we also have people on ladders as something that you might commonly encounter in an orchard, but might not think about. For the people lying down and falling down, we use mannequins to collect those to ensure the safety of all the people participating, but would put the clothing, or at least the shirts of the people who had been doing the rest of the log set onto the mannequin for collecting those data. So finally, we come to a video of what this looks like from the perspective of the vehicle. And this is one of our most challenging logs in the data set. So you can see how well you do on this. You got some pretty significant sun glare as we come around the corner here. As you watch, see if you can detect the person before it's too late. The vehicle will drive down the row and then come to a stop in front of the person. And then there they are. So you've got a person on a ladder off to the side there. So I'll let that play and loop, and I'll pause for our first set of questions. Do we have any queued up?
So does anyone have any questions? Currently, there aren't any waiting in the chat box. Well, I had a question when I read the papers. When I saw how long the study had been going on, that you had collected data for 3 years. That's right, isn't it, Zach?
Yeah, at least the data collection trips were spread out over that amount of time. They started up, yeah.
Did you intend to create this kind of study in the beginning, or was it after year one you thought, well, maybe we should? Or, I mean, that's a really long time to be collecting. I mean, how did you? I mean, these projects sometimes they take a life of their own. You know, how did you? How did it How did it come about? Yeah.
The earliest parts of the data collection were motivated by the commercial project, the development of the autonomous tractor system and evaluating it. And then when we got the government funding to continue it, we did additional data collections with that system later on. That was a year or so later. And then, yeah, continued collecting over another year. So that was a 2-year project there.
Okay.
And then we got permission to include the previous data from our sponsors. So it has been a pretty long time putting it all together, but you need that to be able to get both just like sheer volume of data that you need to evaluate and the variety of conditions that we're able to represent here.
Right. Okay, and then some questions came in. So you may cover this in the future, but one question was, how was the data annotated?
Yeah, we're about to get to that.
Okay, and then another question. Another question was on said the link on the screen didn't work, but I copied it and it redirected to another link. So I'll send that back in the chat, the redirect link, because I'm getting it to work here.
Okay.
Yeah.
Yeah, the location has moved, but it's supposed to redirect, but there is a link to the most recent URL for it in the conference notes as well.
Yeah, okay. And then there's one more on the hardware. So what kind of high dynamic range camera and what was the dynamic range?
We're not sure exactly what the dynamic range is. These are a model of camera that does not actually exist on the market anymore. These are Pixum, I think they're called T-Wolf cameras.
Yeah, I think that's right.
And what their claim to fame was that individual regions of the camera could actually be sampled at different rates. So it was actually, although you get out regular dynamic range, it's still only 256 bit depth. You are able to have some things are actually representing more light than other pixels. I think their tagline was something like a camera for every pixel or something.
Okay. And then we have one more. Obviously, there needs to be some limit to data collection, but were there any particular aspects of people that you considered or would have liked to capture but didn't? For example, children, different body types or heights, different ethnicity, etc.
Yeah, that's something we definitely thought about.
Throw in something else.
Yeah. It's definitely something we thought about. For ease of logistics, we used the engineering team as all of the subjects in it. So it is quite limited in that way. That's something that we are aware of and would love to look at in future work if we found the funding for it. But it is entirely male, Some sections are very heavily white, all adults. So that's true. Farms definitely have much more variety than this data set. It's quite common for kids to be working on them. We do not claim that this data set will get you all the way to a fieldable system. If you did want to field something, you would need to go to the extra step of collecting all that variation.
Okay, so let's go on to the next section then. I'll mute my.
All right, continue on. Evaluation. So yeah, now let's get into annotation of the data. So the labeling scheme that we used is one mimicking the Caltech data set. So illustration of that in the video here, where you have the white rectangle representing a bounding box around the location of the person in each image. One significant difference that we have from Caltech, though, is we were representing just the visible portion of the person, whereas they try to label the entire extent of the person, even if it's not visible. Yeah, we thought that was more difficult to accurately do, and rather focus on the things that you can actually see and know for sure where they are. We also use a tool that allows you to just label a few frames of the video and interpolate between them to label the entire video to speed up the process. We break down the entire data set into train, test, and validation sets, where we would take the sets of logs that I described before that consist of all the different poses and motions of a person in a single outfit, assign each of those sets to one of the train, val, or test subsets, and break things up in that way. And so we tried to keep about half the data for train and then a quarter each for testing and validation. It's a pretty large validation set by most standards, but we wanted to make sure that you could really train on the training data and then do all of your algorithm tuning on the validation set. You'd have plenty of data to fully evaluate your model on validation set and never have to touch the test set until you're completely done, and then run on that to evaluate your true performance. So you can see stats of how things break down there, but you get quite a few of these full sets of logs in each of those sets. And then we also have negative logs that are partitioned similarly, same ratios. Then once we have ground truth bounding boxes and detections from the algorithms that we're evaluating, you have to decide how do we determine whether a detection is correct or not. So the standard way of evaluating that is to, compare the two boxes and compute their intersection over the area of their intersection divided by the area of the union of the two boxes, and then put a threshold on that. So a pretty standard threshold to use is 0.5, so you have to have at least half of the area in the intersection. But you can choose other thresholds as well. So we show on the left here illustration of a few detections. On the top is a few detections that are just barely rejected by a threshold of 0.5. So those are considered not quite good enough. Then if you loosen the threshold to 0.3, the bottom row shows what those look like. Those are also ones that are not quite good enough for a threshold of 0.3. So you may look at those and say, oh, those are actually pretty good detections. I could work with those. And the right choice there is going to depend on the task that you're trying to address. So hold that thought. We're going to come back to that. First, I need to explain a little bit about how to evaluate things in aggregate. So for the moment, assume we've made a choice of an overlap threshold of 0.5. And for all of the plots of this sort that I'm going to show, they correspond to choosing that pretty standard 0.5 value. So these are ROC plots, the way that the vision community typically evaluates performance in this domain. The y-axis is miss rate, so how often you fail to detect the person. So you want that to be low, obviously. And then the x-axis is false positive rate, which says how often are you producing detections when there's no person actually there. And notice that that's on a log scale. So 10 to the -3 means that on average you produce a false positive detection every 1,000 images, not very often. Then it's moved to the right, 10 to the -2, every 100 images, every 10 images, and at the extreme case, 10 to the 0 is a false positive on average in every image. So we focus on this region between 10 to the -3 and 10 to the -1. That seems like where you would want to be at the worst for fieldable systems. So yeah, you want to be down and to the left on all of these, and then the curves here correspond to each of the algorithms that we're evaluating, and a sweep of the sensitivity values associated with basically putting a threshold on the strength of detection for each of the algorithms, and you can see all of the realizable trade-offs between miss rate and false positive rate for each algorithm. So for instance, the green curve here that corresponds to that algorithm, which I haven't talked about yet, but I will later, is strictly worse than all the other three for every choice of sensitivity. But these other ones are kind of intertwined. So that is the plot of ROCs. Now back to the question of threshold on overlap. We compute a single number for an overall score for performance, which we call average detection rate. And that is based on first computing basically the integral of the curves, of the ROC curves, so area under each of those. And then we compute that curve for several different choices of the intersection over union threshold, ranging from 0.3 at the low end up to 0.7 at the high end, and average those scores to get a single overall score. So that allows a kind of sliding scale of sensitivity to localization accuracy that still lets us evaluate ones that algorithms that don't localize particularly well but detect very consistently, but rewards those that are able to localize extremely well. So now to the algorithms that we evaluated in the first paper. So we took a few leading algorithms and our own novel detector that we developed over the course of that work and compared them. First one is DetectNet, which is just an off-the-shelf algorithm that NVIDIA provided that's just really easy to get up and running to provide kind of a baseline for what you can do with very little effort. And then we took two state-of-the-art algorithms that were the leaders on each of the most prominent person detection benchmarks that had code available and evaluated them as well. So that's Reason Proposal Network with Boosted Forests and Multiscale CNN from Kitty. Our RPMDF was the leader in South. And since this talk is focusing on the data set, I'm not going to talk about our novel detector, but you can see the paper for lots of detail on it. It does do quite well. Now we'll get into results. So we actually hop back to the ROC that I've already showed to talk a little bit more about the performance of the individual algorithms here. So this is the overall what we call the baseline data set that's evaluating on almost all of the data in the data set. And you can see kind of the main trends of, as I said already, DetectNet does pretty poorly compared to all the other algorithms. RPNBF, I think, is strictly worse than MFCNN, but it's hard to say. Well, you can't say that MFC is strictly better than either of them, though for most of the plot, it is the lowest one, as you would want it to be. We also have several ways of evaluating on subsets of the data set to understand where that performance is coming from and what specific areas of or situations you do better or worse on. So we have scale, occlusion, motion, and pose annotations available in the data, which are encoded in the names of the logs in the data set. And our evaluation tools also automatically process them to allow us to evaluate performance on each of these subsets. So first, motion versus static, you can see actually not a whole lot of difference in the performance in general of these algorithms on people who are standing still versus people who are in motion. The curves don't move that much. It seems that people in motion are actually a bit easier in general. Performance is a bit stronger on them than standing people. If we look at different levels of occlusion, there are dramatic changes there. So we divide it into 3 bins of occlusion. People who are more than 70% of them is visible. People who have between 30 and 70% visible, which we call partial occlusion, and people who are less than 30% of them is visible is heavy occlusion. And you can see performance drops off in big chunks as you move from clear to partial to heavy occlusion. But in this heavy occlusion case is one of the places where MFC starts to pull away from the rest of the pack. We can also look at different scales of people, well, scales of bounding boxes, really. So these are evaluated based on the area of the bounding box of the person. So large ones are greater than 3,500 pixels, small ones are smaller than 1,300, and medium is in between those two. Large versus medium doesn't have a particularly large impact, but when you get into the small people, performance drops off for all of the algorithms. Though much less so for MFC than the other ones. And then the different poses are also one where you see some pretty big differences. So the typical poses are the people standing or crouching, and then the unusual ones are the ones of people lying down or on ladders. Those ones in particular have different aspect ratios, which can be challenging to a lot of algorithms, but MFC actually does extremely well on these challenging conditions. So putting all of that together, we can evaluate the average detection rate on all of these. So the ROC curves that I was showing on the previous slide are one choice of that overlap threshold, but this is the metric that evaluates our averages over all of those different thresholds in the range. And you can see that the general conclusions still hold as you do that generalization. MFC ends up winning for all of the categories except for one. MFCNN edges it out on large scale people by just a little bit. But maybe more intuitive is to see these algorithms in action. So here is a video of the detections on a portion of our test set. This video is 5 minutes long. The entire test set shown the same way is just about an hour long. There's a lot of things going on the screen here at once, so let me step through them. First, the white rectangles that you see in each of the images are the ground truth annotations of the location of the person. And then the red, green, and blue bounding boxes are detections from the 3 leading algorithms, MFC, MFCNN, and RPNBF. You have two different images here. Left and the right correspond to two different choices of sensitivity threshold. The left corresponds to a average false positive rate of 1 every 100 images, and the right is 1 every 10 images. So you can see how the performance varies with the two different choices. And then down at the center bottom of the image, you can see the annotations of the metadata of each of the categories associated with each image. So saying which environment it came from, level of occlusion, the scale of the person in that image, whether it's a normal or typical or unusual pose, and whether they're standing or static or in motion. So I'll let this continue to play and pause again for a second round of questions before I hand it over to Trent for some of the follow-on work.
Okay. So we had a couple of questions. So one of the questions was what percentage of the images were people in an odd position? So for example, the ladder example.
Yeah, so I can tell you, where is, okay. Oh, this is actually the wrong part. If I go back to here, it is a pretty small portion in the orange data, a bit larger in the apple data, around close to maybe 18% of the images are the unusual poses in the apple data, and probably around like 7 or 8 in the orange data. And that's a combination of lying down, falling down, and on ladders. I don't know the breakdown within those, but it's certainly more of people lying down than on ladders. So we do a few different variations of that.
And the biggest explanation for this is that the data collections were not continuous. These were things that we added in later collections.
Mm-hmm.
So it was the last trip to oranges that we added these falling down and lying down. And then when we went to apples, we added ladders. And there was plenty of orange data which did not have falling or lying down from an earlier year.
Mm-hmm.
I see. Okay. And then the next one is regarding the observation that moving people are a little easier to detect than static people. Is this because their limbs tend to be more separated, or is there another hypothesis?
That's pretty nearly our hypothesis, that we think it's our moving ones quite often are away from the trees. They're not always in a really hidden spot.
Mm-hmm.
You can't really move around if you're really deep in the tree. So just because of that, there is a sampling bias that most movement takes away, or happens at least a short distance from the tree.
Okay, and then the last one was the stereo data actually used in the CNNs, or were you treating the images individually, or how was that?
Yeah.
How is that dealt with?
These detectors are not making any use of the stereo data at the moment. None of them do that, and they treat each image independently. So they're not making use of the continuous video either.
And in the kitty data sets, go ahead.
If you try something that does make use of that, that would be great, and you can submit it to the benchmark.
Yeah, in the kitty data set, they are available, and they just have flags in the benchmark list that says use motion data or use stereo data. If someone submits to us that uses one of those, we're definitely open to putting that on our website as well, that this did better but use stereo data.
So in the on the kitty side, on the like urban pedestrian detection side, some people have used the stereo data as well. Is that right?
That's right.
Yeah.
Okay. Yeah. I mean, I don't follow that side. I'm more on the ag side. Okay. And that covers questions for now. So I'll mute myself and let you carry on.
I'll hand it off to Trenton for the remainder of the talk.
Hello, as Zach said, I'm Trenton Tabor. I'm also an engineer here at NREC. I'm going to be going over some work that we presented at Safety, Security, and Rescue Robotics this year. We took this data set and we started to examine what are some alternate uses besides just evaluating raw performance. So first off, I'll say we did spend a lot of time in that work evaluating performance of many more detectors. So I think that there are 7 detectors that we started evaluating that were not in that previous work. And you can see very similar plots to what Zach showed before. And just get a sense of that we are looking at a much larger stable of detectors in this new work. But we first start by looking at them the same way. One of the interesting ways that this work came about is we actually partnered with another group at Carnegie Mellon that does a lot of work on safety and robustness testing. I'm just showing a real short video from some of their prior work where they were able to cause a collision checker and motion planner to ignore constraints and cause a robot in simulation to try and damage itself. That robot actually ended up damaging itself a few months later because they didn't take the fixes that that team recommended. But they were very interested in how can robustness testing ideas be translated to computer vision. And some of the things that we thought about was perception systems are way too high dimensional to be able to just create out of thin air new inputs that you could test with. So what we came up with was an idea of mutating nominal inputs in reasonable or even physically realistic ways and then testing with those. So I said physically realistic or physically grounded in the slide. So I want to go over a little bit what we mean for this. So first, we spent some time doing literature review of common imaging degradations that occur in the real world. We then implemented parameterized versions of these, and then we used these mutated images to perform the same types of evaluation we have been performing. And then we went one step further to use these to evaluate robustness. So when I mention the physically realistic ones, here's some of the examples of the easier ones that we implemented. If you look at the paper, you'll see some more justification for each of them. And then we also implemented some more interesting, from our perspective, ones that actually make use of geometry of the scene. So both haze and defocus require depth estimates and are both obviously very common in real-world imaging scenarios. So what we did with these is apply them to our test set and look at how performance changes. So if you look at the top row of images here, those are images from our test set and detector performance on them. So you'll see the detector had no false positives, and we looked at the bounding box, no false positives was kind of a misnomer there. We looked at the bounding box that best detected the person, and we looked at what would be the equivalent false positive rate to have included that bounding box. So for those 3 images at the top, you see that in order to have included those detections, you would need fairly low false positive rates. One is every other image, another is every 200 images, and the last one is like 1 out of 8 images or so. And we then applied a very small mutation, and that's actually in the image below. I bet that many people who are viewing this online will not be able to see a difference in images between the top and bottom. But what you'll notice is the false positive rates required in order to detect the people in the image go up substantially. So it now is the case where the detections are all at strength 0. So it's actually the same equivalent false positive rate for all of them. But you would have to accept the equivalent of 400 false positives per image in order to have detected the person in these very, very lightly modified images. So these are, of course, cherry-picked. These were the very worst cases of changes we saw, but we still found that pretty illuminating. But obviously, the more principled way is to look at things in aggregate. So here is one example. Again, we chose something pretty extreme, so it'd be obvious. So this is a different mutator. This is channel dropout. We looked at the same type of average detection rate that Zach described earlier. You'll see that the 8 methods we have here have, in most cases, pretty similar performance, although the SSD methods are meant to be fast as opposed to accurate, so they're much lower. And we then drop out one of the color channels if you assume that this image was encoded as YCBCR, which is pretty common for transmission and compression. And we looked at how did these average detection rates change. So you'll see written is the actual new average detection rate, but then it's colorized. I think that'll come up. There we go. It's colorized to show how much it was actually affected. So dark blue means that the detector was not at all robust to this change. It went from some reasonable average detection rate to almost 0. There is also, I don't think on this picture, but on other pictures, a real, okay, in this one, there is one example where there's a bright yellow where performance actually improved very slightly if you drop the red channel for MSCNN. But we found this to be quite interesting because you can see the colors are highly dependent on which detector you're evaluating. So some detectors are more or less robust than others. Here's another example from one that's much less extreme. This is our model-based haze that we used. And you'll see that for most detectors, there was not a huge amount of change. But you'll see that MSCNN, which had been something we brought with us from our previous work, did have a big drop in performance. So I would probably not recommend that one if you need to be robust to haze. So we did this for all of the combinations we had of detectors and mutators and even parameterizations of mutators. So I'm going to zoom in on one kind of section of the graph here. You'll notice that faster RCNN with inception ResNet and deformable RFCN have the same baseline performance, 0.71 average detection rate for both. But if you look in aggregate at the robustness characteristics, the deformable RFCN actually has a much bigger drop in performance when you have channel dropout. And you see in a couple other places it also starts to fail earlier than faster RCNN with inception ResNet. So we obviously found that quite interesting. This might have affected your choice of what detector to use in the field, even though the standard methods would have told you that they are basically identical. So just going to summarize this little section. So as we saw, very, very small image changes, even when they're not adversarial, they're physically realistic, can have very big effects on detector performance. We even saw that these can have effects not just on one image, but in aggregate across the entire data set. And we have now kind of introduced a way of detecting or evaluating robustness with respect to each of these mutations. And we do have ongoing work to see how can we apply that robustness in more interesting field relevant ways. So before we break for our last set of questions and wrap up, I do want to point out this is one follow-up work we did, but there's actually a lot of other directions people can go based on the data that's available. So I mentioned haze and defocus require depth estimates. So we do have the right and left image both available. So you can do things like evaluate the qualitative performance of stereo reconstruction, or you can even use that for SLAM algorithms. So this is an example of the mesh that we get when we do the defocus or hazing on a couple images from our data set. And you'll see that the mesh is pretty complete. It's quite dense. We were very happy with how that turned out, even with this very difficult imaging situation. Then we point out that since we have consecutive frames, it's totally reasonable to use motion-based features in your detections, or to do tracking between images, or to use this for a qualitative evaluation of things like optic flow. Similarly to optic flow, there's other approaches you can test with this, like visual odometry, and I'll get to that more in detail in a moment. But in order to test those things, you obviously need positional ground truth. So we provide in our paper a calibration between the camera and the GPS, as well as a trajectory in the camera frame that we corrected using those same parameters. So that's perfect if you want to do a visual odometry tuning or testing. So it is a totally reasonable thing to take our training set and tune your visual odometry algorithm and then apply it to our validation and test set. Just as an example for this talk, we did try one quick visual odometry evaluation using one of our state-of-the-art VO algorithms. And we compared it to one of our longer logs in the bottom there. So you can see that you have, looks like a few hundred meters of traverse, which is associated with ground truth, extremely valuable to VO folks. All right, so I think that that wraps up our presentation. Obviously, it takes a lot of folks to build a data set like this. So as I mentioned, Zach and I are the ones on the line. We also had a couple of interns, several faculty associated with this effort, and many staff members. We have many positions in all of those things. We're hiring special faculty, postdocs, staff, interns in our agricultural as well as other commercial work. So please let us know afterwards if that's something of interest to you. And obviously, our work would not be possible without our funders. So I'll just repeat, we're very, very grateful to the USDA and the Army TRMC for supporting all this work. And I think that's our last break for questions.
Okay, so we had one more question come in. From Nathaniel, were the modified images included in the actual training data set when training each one of the CNNs? And okay, so in the paper that Trenton presented, and would that make the CNNs more capable in the impaired environments?
That's
or did you only
obviously
test
the most
on the mutated?
Common question we get. On this work, that's the most common question we get. We intentionally chose not to train on these things. We kind of have a philosophical problem with trying to over-optimize to these things, that you only are going to have access to the set of degradations that you think of beforehand. And obviously that's not going to be full coverage of the set of degradations you're going to see in the field. So yes, you could easily pull any one of these into the training set and immediately your loss in performance will go away on them. But we're not just interested in how do you do on the known unknowns, we're much more interested in how do you do on the unknown unknowns. So we see this as a proxy for all the degradations you didn't think of. And we are, in future work, hoping to pull in more degradations, but we intentionally do not train on these things because then we would have given up our best tool at evaluating more general performance.
Okay. So are there any other questions? All right, so thank you very much, Zach and Trenton. Thank you for being the first webinar. And if anyone wants to give a webinar, please contact me. I'll be very happy to talk to you. And with that, we'll close. Thank you all.
You all.